Well, I chose this problem because it looks scary, but I wanted to hopefully encourage you that even though it might look scary with all these crazy diagrams, if you carefully consider each question and what principle of physics they're getting at, um, you will probably, hopefully, be able to solve the problem. So let's go down to the first question where we're just supposed to be drawing a vector that represents the direction of the electric field at R and S. And so here the idea is that it says it's a positive volume charge density. And so that means within this Gaussian surface, it's all positive charge in there. And remember, the electric field at a certain location, actually I should say the flux at a certain location, really only depends on the enclosed charge. And so since the enclosed charge is positive, you would expect that the electric field vector would look something like this. And so that's going to be your answer for R, the electric field points up, and for S, the electric field points down. So now we have to find flux. So really we only have two equations that have flux in it. So the one equation is the definition of flux, which is EA cosine theta. The other one is Gauss's law, which says that the flux is equal to the Q enclosed over epsilon naught. One of those two is going to do it for you, and it's going to be this one in this case, because we do not know what the electric field is. But we do have a way of figuring out what the enclosed charge is, because we can use the volume charge density. Remember, the definition of volume charge density is Q over V. And so if we input the symbol they gave us, rho sub 0, and we're looking for Q enclosed. We need to know what Q enclosed is in order to use this formula. So I'm going to substitute Q enclosed for Q. And what's enclosing the Q? It's the Gaussian surface. So down here, this would be the volume of the Gaussian surface that they drew. So the Q enclosed is equal to rho sub 0 times the volume of the Gaussian surface. Now, that surface is a cylinder, and the volume of a cylinder is basically the area of an end cap multiplied by the height of the cylinder. So in this case, it's just A times H. And those are symbols we're allowed to use. We're allowed to use A, we're allowed to use H in our answer. So that's the Q enclosed. And so finally then, to get the flux, it's the Q enclosed, rho sub 0 AH over epsilon naught. So that would be the answer to part one of part B there. Now we have to figure, actually we don't even, well, yeah, we have to, they tell us what the answer is. It's always nice when they tell you what the answer is, but we have to prove that. So that's going to come from our other equation for Gauss's law right up here. So let's work with that. I'm going to substitute in our expression for flux, rho sub 0 AH over epsilon naught. And typically, you can use something from just the previous part of the question in your current answer. Lots of times, a previous part is setting you up to be successful on the next part, and that's one of those cases right here. We're looking for E. Now, A, what's A? A is the surface area of the Gaussian surface, but it's only the surface area that actually has flux passing through it. If you go back and look at that picture, the side walls of this cylinder do not have flux passing through them. The electric field lines are parallel to the side walls. So it's only the two areas, both of them. So I'm going to do 2A. Those are the only two things that have flux passing through them. And so it looks like A is going to cancel out. And this simplifies to E is equal to rho 0 H over 2 epsilon naught. The only problem here is notice that H doesn't appear in this answer, but Z does appear. So we got to substitute H with some form of Z. And if we go back and look at the picture, Z represents, some point on the Z-axis. And in this case, if Z is up here, if Z is at the top of the cylinder, then the bottom of the cylinder is equally below 0. So I'm just measuring, from 0. And so in terms of a magnitude, that means the total height of this cylinder is 2Z. The total height of this cylinder is 2Z. And so let's substitute that in. So this is rho sub 0, 2Z over 2 epsilon naught. The 2's cancel out, and we just proved what they were asking us to prove. So we were successful with that. Okay, now they're putting the slab in between parallel plates that have some charge on them, and they're asking us where the electric field might be equal to zero. So here it's helpful to draw some electric field vectors. The electric field from the slab points outward, as I explained earlier, because it's a uniform positive charge inside of there. But the electric field from the plates is also present, and that points from the positive to the negative plate. So these are the red vectors. So when you look at this picture, the only place where those vectors are in opposite directions and therefore could add up to zero is in this region right here. And this region is underneath zero. It's in the negative numbers. It's less than zero. So this is our answer right here. And when it says justify your answer, pretty much what I just did verbally is just drawing a picture and indicating that this is the only region where the vectors can cancel out. Now they want us to calculate this value. So that really that means where the electric field due to the slab is equal to the electric field due to the plates. And we already figured out the electric field due to the slab. That was, and even if you didn't figure it out, they gave it to you. And that was the rho sub zero, I want to get this right, Z over epsilon naught. And the electric field due to the plates, what's that equal to? Well, hopefully, I mean, this is a good thing to memorize where you can look back in your notes. But when you have parallel metal plates, the electric field between them is sigma over epsilon naught. I mean, you can derive that using Gauss's law, but it is helpful if that's something that you remember. I'm just double checking my formula. Yeah, that one's right. Okay. So, the epsilon naughts cancel out, and so it looks as though Z is equal to sigma over rho sub zero. And since they actually give you some values for this, you should go ahead and calculate that actual number. So sigma is 2 times 10 to the negative 6, and rho sub zero is 1 times 10 to the negative 3. I can actually do this one in my head because 2 divided by 1 is 2, and 10 to the negative 6 divided by 10 to the negative 3 would be times 10 to the negative 9th. And I'm doubting myself because that seems small. I feel like I made a mistake somewhere. Two times 10 to the negative 9th. Okay, I'm back. See, I got all cocky there and told you I could do it in my head, and I made a mistake with the exponents there. It should be, since I'm dividing, it's negative 6 minus negative 3, which is not negative 9, it's negative 3. So this should be 2 times 10 to the negative 3. But you know what? That's a good lesson that when you're calculating an answer, look at the answer and see if the number seems reasonable. And to me, 10 to the negative 9th, which is nanometers, like the size of an atom, that just looked wrong. And that was a little cue that I should go back and check my math. And yes, this would be in meters. So that's going to be your right answer. What else do we have to do? One last task. The magnitude of the potential difference. Okay. So you got to think about your potential difference formulas, and also think about the fact that we've been working with electric field for a while. And so what comes to my mind is that delta V is equal to the negative integral of E dot ds. And furthermore, actually, I was going to say that this is a uniform electric field, but only the one due to the plates is. So we're going to have to do this integration. Now, by the way, do yourself a favor. It says magnitude. Let's just not even worry about that negative sign. So what I want to do is, first of all, put in an expression for the electric field. So we really have two electric fields. We have the electric field due to the plates, which is sigma over epsilon naught. Plus, we have the electric field due to the slab, which is rho 0 Z over epsilon naught. And I do have a plus sign there because this is from the center of the slab to the top, and that's the region where both those electric field vectors point in the same direction. So I should be adding them together. I'm going to use as my linear variable Z instead of S. That's totally legitimate. And that's what we have to integrate. And we're integrating from 0 to the top of the slab. And we're actually going to use numbers here. I believe it says that they are separated by a distance of 0.01 meters. And so that means from the middle to the top would be 0.005 meters. So that's going to be our limits of integration. So really we have two separate integrals here. This is a constant. There's no variable there. So when you integrate that, we're just going to have sigma over epsilon naught z, because the integral dz is z. This one here does have a z in it, so we are going to have to integrate that. So we're going to add 1 to the exponent, which makes it z squared, and then we're going to divide by that new exponent. So we're going to have 2 epsilon naught there. And as I said, our limits of integration are from 0 to 0.005. So to finish this thing up, you just basically have to put in all of the relevant numbers there. So sigma, they said, is equal to 2 times 10 to the negative 6th, 2 times 10 to the negative 6th, epsilon naught, 8.85 times 10 to the negative 12, z is 0.005, and rho sub 0 is 1 times 10 to the negative 3 times 10 to the negative 3. Again, z is 0.005. Square that over 2, and epsilon naught is 8.85 times 10 to the negative 12. So if you bang that out on your calculator, I'm looking for my calculator, you can probably turn off the video at this point, because the rest is just doing these calculations, but I want to do it just to make sure I get the right answer. 0.005, 8.85 times 10 to the negative 12. Okay, and then 1 times 10 to the negative 3, 0.005 squared, divide by 2, divide by 8.85 times 10 to the negative 12. Add those two things together, and I get an answer of 2,542 volts, which I think is the right answer. So, all right, there you have it.